Space is vast and full of mysteries. Among the many wonders of the universe are the forces that shape it. Gravity is one of these forces. It holds our planet in orbit around the sun. It also governs the interactions between all celestial objects. The universe is a place of incredible beauty and immense scale. It's a place where giant planets orbit distant stars. It's also a place where tiny moons dance around massive gas giants. Sometimes these celestial ballets have dramatic consequences. This brings us to the fascinating concept of the Roche Limit. The Roche Limit is a critical threshold in the cosmic dance of gravity. It determines the fate of celestial objects that venture too close to more massive bodies. Join me on this journey as we unravel the secrets of the Roche Limit. Imagine a cosmic game of tug-of-war. On one side, you have the gravitational pull of a planet, trying to hold itself together. On the other side, you have the tidal forces exerted by a nearby star or a massive moon, trying to pull the planet apart. The Roche Limit is the critical distance at which these forces reach a stalemate. Named after the 19th century French astronomer Édouard Roche, it's the distance within which a smaller object held together only by its own gravity will disintegrate. This disintegration happens because the tidal forces exerted by the larger body exceed the gravitational force holding the smaller object together. It's a crucial concept in astrophysics because it helps us understand the distribution of matter around planets and stars. It also explains the formation of some of the most spectacular phenomena in our solar system, such as the rings of Saturn. To truly grasp the concept of the Roche Limit, we need to delve into the science behind tidal forces. Tidal forces arise because gravity weakens with distance. The side of an object closest to a massive body experiences a stronger gravitational pull than the side farthest away. Imagine the Earth and the Moon. The Moon's gravity pulls more strongly on the side of the Earth facing it. This pull is weaker on the opposite side. This difference in gravitational pull stretches the Earth slightly, creating a bulge on both sides. The same principle applies to any two celestial objects. The difference in gravitational pull across an object creates tidal forces. These forces can be incredibly powerful, especially when objects are close together. This is why the Roche Limit is a critical distance. It's the point where these tidal forces become strong enough to overcome the gravitational force holding the smaller object together. The concept of the Roche Limit bears the name of its discoverer, the French astronomer Édouard Albert Roche. This fundamental principle in celestial mechanics has become a cornerstone in our understanding of gravitational forces and their effects on celestial bodies. Born in Montpellier, France in 1820, Roche dedicated his life to studying celestial mechanics and the intricacies of gravity. His early fascination with the stars and the mechanics governing their movements set him on a path of scientific discovery that would leave a lasting impact on the field of astronomy. In 1848, at the young age of 28, Roche published his groundbreaking work on the limits of gravitational stability within binary star systems. This publication was a significant milestone, marking the beginning of a new era in the study of celestial mechanics. His calculations revealed the critical distance at which a celestial object, held together only by its own gravity, would be torn apart by the tidal forces of a more massive companion. This discovery was crucial for understanding the dynamics of binary star systems and the forces at play. Roche's work, initially focused on binary stars, had profound implications for understanding the stability and evolution of planetary systems as well. His insights extended beyond stars to include planets and their moons, providing a comprehensive framework for celestial mechanics. His calculations provided a framework for explaining the existence of planetary rings, such as those around Saturn, and the formation of moons from the accretion of smaller bodies. This was a significant leap in our understanding of how complex planetary systems develop and evolve over time. Despite his significant contributions to astrophysics, Roche remained a modest figure throughout his life. He was deeply respected by his peers but never sought the limelight, preferring to let his work speak for itself. His work on the Roche Limit, however, remained his most enduring legacy, solidifying his place in the annals of astronomy. Today, the Roche Limit continues to be a fundamental concept in the study of celestial mechanics, a testament to Roche's lasting impact on the field. The Roche Limit is not just a theoretical concept, it has profound real-world implications, shaping some of the most captivating phenomena in our solar system. This invisible boundary determines the fate of celestial bodies that dare to venture too close to a planet. Two striking examples of the Roche Limit's influence are the rings of Saturn and the dramatic demise of Comet Shoemaker-Levy 9, both of which offer a glimpse into the dynamic processes at play in our cosmic neighborhood. Saturn's rings, a celestial ballet of ice and rock particles, are a testament to the power of tidal forces. These rings are not just beautiful to look at, they tell a story of destruction and creation. These rings are believed to be remnants of a moon, or a large comet that ventured too close to Saturn, crossing the planet's Roche limit. The gravitational forces at this boundary are so strong that they can tear apart even the most solid objects. The immense tidal forces rip the object apart, shattering it into countless fragments. This violent process is a stark reminder of the raw power that governs our solar system. These fragments continue to orbit Saturn, forming the majestic rings we observe today. Each particle, from tiny ice crystals to larger rock chunks, plays a part in this ongoing cosmic dance. Comet Shoemaker-Levy 9 provided a more dramatic display of the Roche Limit in action, showcasing the destructive potential of these tidal forces on a grand scale. In 1992, this comet made a fateful close encounter with Jupiter. The gravitational pull of the gas giant was too strong for the comet to withstand. As the comet made its final plunge towards Jupiter in 1994, it crossed the planet's Roche limit, breaking into 21 fragments. Each fragment was a piece of the comet's shattered core. These fragments slammed into Jupiter's atmosphere, creating colossal fireballs and leaving dark scars visible for months. The event was a spectacular reminder of the dynamic and sometimes violent nature of our solar system. What happens when an object crosses the Roche limit? The answer, as we've seen with Saturn's rings and Comet Shoemaker-Levy 9, is a dramatic and often destructive process. As an object approaches the Roche limit, the tidal forces acting upon it begin to overwhelm its own gravitational force. This difference in gravitational pull across the object causes it to elongate, stretching it towards and away from the larger body. As the object moves closer to the Roche limit, this stretching becomes more and more pronounced. Eventually, when the tidal forces exceed the object's internal strength, it can no longer hold itself together. The object breaks apart, shattering into numerous smaller fragments. These fragments, still bound by the gravity of the larger body, continue to orbit within the Roche limit. The fate of these fragments depends on their composition and size. The Roche limit is not just a phenomenon confined to our solar system. It is a universal principle that applies to celestial bodies across the universe. It plays a crucial role in shaping planetary systems throughout the cosmos, influencing the arrangement and stability of moons, rings, and even planets themselves. As we discover more exoplanets, the Roche limit becomes an essential tool for understanding their formation, evolution, and ultimate fate. It helps scientists predict which celestial bodies can remain intact and which will be torn apart by gravitational forces. For instance, the Roche limit helps us determine the minimum distance at which a moon can orbit a planet without being destroyed by tidal forces. If a moon forms too close to its host planet, within the Roche limit, tidal forces will prevent it from accreting into a stable body. This is why we often see rings around planets like Saturn, which are made up of particles that couldn't form a moon. This has implications for the potential habitability of exomoons, as moons outside the Roche limit are more likely to have stable orbits and potentially suitable conditions for life. These stable orbits allow for the development of atmospheres and possibly even life. The Roche limit also helps us study the composition and history of exoplanetary rings. These rings can tell us a lot about the past interactions between celestial bodies in a planetary system. By analyzing the structure and density of these rings, astronomers can infer the nature of the objects that were torn apart to create them. This information is crucial for understanding the history and evolution of planetary systems. This provides valuable insights into the processes of planet formation and the dynamics of planetary systems, helping us piece together the complex puzzle of our universe. Our own moon, a constant presence in our night sky, raises an intriguing question. Could it ever cross the Earth's Roche limit and meet a cataclysmic end? Rest assured, the answer is no. The moon orbits the Earth at an average distance of about 384,400 kilometers. This is well beyond the Earth's Roche limit for an object with the moon's density, which is estimated to be around 1737 kilometers. In fact, The moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year. This drift is caused by the tidal interactions between the Earth and the moon. As the moon's gravity creates tides on Earth, it also causes Earth's rotation to slow down very slightly. So, instead of getting closer and risking crossing the Roche limit, the moon is actually moving farther away from Earth. From the majestic rings of Saturn to the fiery demise of Comet Shoemaker-Levy 9, the Roche Limit has shaped some of the most captivating phenomena in our solar system. It stands as a testament to the power of tidal forces and the delicate balance of gravity that governs the cosmos. Beyond our solar system, the Roche Limit plays a crucial role in understanding the formation, evolution, and fate of exoplanetary systems. It helps us determine the stability of moons, the composition of planetary rings, and the long-term survival of planets orbiting close to their stars. As we continue to explore the universe and unravel its mysteries, the Roche Limit will remain an essential tool for astronomers. It will guide our understanding of planetary systems, their formation, their evolution, and the intricate dance of celestial objects under the influence of gravity. The Roche Limit is a reminder that even in the vastness of space, fundamental physical laws govern the interactions of celestial objects, shaping the cosmos into the wondrous tapestry we observe.